Hi, everybody. Welcome to the second live session on this numerical analysis course in NPTEL. I'm Baskar, the instructor of the course, and I'm today with Mr. Shubham. He is our TA. So how many students? Okay, so there are 5 students. So welcome you all. I hope more will join. So I hope you are enjoying the course. If you have any difficulties or any suggestions, you can tell us. Otherwise, we can just go on with our discussion. I'll just give you 2 minutes. If you have any suggestions or questions, you can ask us. Am I audible to you? I'm not sure whether we are audible. So, am I audible? Can one of you just confirm whether we are audible to you or not? Yeah, so good afternoon, and am I audible? Can you just tell me? Am I audible? Okay, so at least one of you responded. Good. Let me just go ahead and okay, so we are audible now. Okay, so if you have any questions, you can ask us. Otherwise, we can just have a general discussion on what we have covered in last few weeks. You can ask any question, like if you have any general difficulties or any suggestions or any subject-wise questions also you can ask them. And thanks for your compliment that it's a good course. I hope you are enjoying it. Okay, so I think in the last week we have in the last live session we just summarized up to uh, maybe the direct methods, and just started at that time. I think we just started matrix norms. So today we will try to just summarize from matrix norm to what we did up to today. See, we have in the second main chapter of our course, we have taken up some linear algebra problems, and we developed some numerical techniques for linear algebra problems. More precisely, we considered linear systems, and we have developed some direct methods like Gaussian elimination method and some LU factorization methods. And then we went on with some iterative methods. Before getting into iterative methods, we have just learned some tools regarding matrix norms. This is because we have to do error analysis on the iterative methods. For that, we need matrix norms, more precisely subordinate matrix norms. We had mainly three subordinate norms. One is L infinity norm, another is L1 norm, and the more physically realistic norm, L2 norm. We also learned how to compute the corresponding subordinate norms for these three vector norms. These are very important. We have also given some tutorial problems based on this. These are like, we have given formulas for them. So therefore, once we give a matrix and ask you to compute the matrix norm subordinate to, say, L infinity norm, it is just the maximum row sum norm, right? So like that, we may give some matrix, ask you to compute some one of these three subordinate norms. Okay, so this is one question that is very important probably. So you have to know all these three matrix norms, I mean subordinate norms. And then based on the subordinate norms, one can also think of computing the condition number. Okay. So we have also covered the concept called condition number of a matrix. Based on the condition number of the matrix, we will decide whether a matrix is a good matrix or not, in the sense that if the condition number is very high, then working with that matrix, more precisely, when you go to solve a linear system with coefficient as that matrix, which has a very big condition number, then it will be very sensitive to even very small errors. For instance, the right-hand side vector B is slightly perturbed. Even then, your solution may be very deviate from the exact solution drastically. Okay, so because of that, one has to understand what is the condition number of a matrix. So computing condition number for a given subordinate norm is also one important question. So we may give a matrix. Say mostly we will stick with 3 by 3 matrix. Okay, so we may give a 3 by 3 matrix, and we will say, okay, use the L infinity subordinate norm and compute the condition number. Okay, so these kind of questions are also very important for you to understand, just to have an idea of how sensitive your matrix will be. Because, of course, in real life, you will not have a 3 by 3 matrix. This is just for the academic training purpose. In real life, people will have a very big matrix, like, even there are problems where 1 billion cross 1 billion matrix you may have to solve, and so on. Okay, so these are just academically we are trying to train ourselves by giving 3 by 3 matrices. So if it is L1 norm, then the subordinate norm is the maximum column sum norm. And then if it is L2 norm, then the corresponding norm is this kind of, it's little complicated. You have to find A transpose, and then you have to find the eigenvalue of that matrix, and then you have to take the modulus and see the dominant eigenvalue of that. Okay. So that's how you can find the L2 norm, subordinate norm, matrix norm subordinate to L2 norm. Okay. So this is one question which is very important from the matrix norm section. Other than that, we also have, suppose you commit some small error in the right-hand side vector, then with respect to that, if you go to find the relative error in the corresponding solution, then how much error one can have maximum, you can find an estimate for the relative error in the corresponding solution. Okay. So that will involve the condition number. So we have a estimate for that. Okay. So we may also give you some, say, 2x2 system. And then we may give some matrix and vector B, and we will just slightly perturb that vector B and ask you what can be the upper bound of the relative error of the solution. So these kind of problems, I think we have already given some problems in the assignment. You have to solve these assignment problems. Not only that, you will get some marks for the assignment problems, because we will also ask some questions either directly or slightly different problem in the exam. Okay, so therefore, solving all the assignment problems, even if you would have solved the assignment problems wrongly, you can still, once the answers are released, you better learn the correct solution of the problems, because these are very important from the examination point of view also. Divyang says, okay, good afternoon. Yeah, good afternoon. Okay, so thank you that you are enjoying the course. That's very nice to hear. A couple of weeks, okay. So nonlinear and maybe we are doing interpolation also, right? So yeah, so it's going on. So okay, good. You are enjoying. So that's very nice. Okay. So we are actually discussing about the matrix norm section. Therefore, to summarize, in matrix norm, you have to learn how to compute the subordinate matrix norm with respect to those three important vector norms. Okay, so we have given those formulas. So you just have to remember, it's very easy formula. So there's nothing to remember in that. Okay, so and then the condition number, and then once you have the condition number of a matrix, if we perturb little bit in either in the matrix or in the right-hand side vector, how that perturbation can make the relative error. Okay, so that is also one that you have to know, how to estimate the relative error of the solution with respect to the perturbation that we may make in the right-hand side vector or in the coefficient matrix. Okay, so these are the main problems that we may focus on from the matrix norm. And also, apart from that, we have given some more problems in the assignment. So you can. Okay, so I should continue something. Yeah. So that's one thing, and then after matrix norms, we have gone into the important chapter on iterative methods. Basically, we developed two iterative methods. One is the Jacobi method, and another one is the Gauss-Seidel method. We have also studied a way to accelerate the convergence speed in any of this method, more precisely with the Gauss-Seidel method, because it is as such a faster method than Jacobi method in many situations. Therefore, we learned how to speed up the convergence through certain relaxation approaches. So that is what is called successive over relaxation method. So we have also learned the successive over relaxation method in this chapter. So in this chapter, the main thing is you have to learn, of course, how, if I give you a system, mostly we will give 3x3 system, or if it is a very difficult problem, then 2x2 system we will give. If it is very direct problem, we'll give 3x3. And we may give some initial guess x naught, and we may ask you to compute one iteration or two iteration depending on the marks. Okay. So if it is Jacobi or Gauss-Seidel like that. And then apart from that, we also have certain convergence theorems, right? So mainly there are two convergence theorems. One is the sufficient condition that if your matrix, given matrix is a diagonally dominant matrix, then surely your iterative method sequence will converge. Whether it is Jacobi or Gauss-Seidel, it will surely converge. Okay. So in that case, we have also seen that the Gauss-Seidel will converge a little faster than Jacobi method when the given coefficient matrix is diagonally dominant. Okay, some question based on this, some here and there, we may just hide this information or ask some questions. Okay. So therefore, you should be aware of this. And it's there is a scope to also ask some questions from the proof of these theorems also. Therefore, in that case, even you need not muck up the proof of the theorem, but you should understand it. Okay. Broad understanding of, because we are not going to ask you to prove anything, because we don't have any subjective questions in the final exam. Okay. Therefore, we will not ask you to prove any theorem, or we will not ask you to write any program, lengthy programs. Okay. So we may just give a program and just hide one or two lines. We may have to just fill up appropriate lines in that kind of question may come. But proofs are not generally asked. But however, in certain fill in the blanks or in some MCQ questions, we may ask some question which may need some knowledge of the proof of some theorems. In that, the sufficient condition is one of the important theorem. And apart from that, we have another theorem which states necessary and sufficient condition, and that depends on the spectral radius of the coefficient matrix. Remember, this necessary and sufficient condition is not on the given coefficient matrix, sorry. It is not on the coefficient matrix. It is on the spectral radius of the iterative matrix. Okay. So you have to compute the iterative matrix and find its spectral radius. Okay. So you have to learn how to write the coefficient matrix for a given iterative method. Say we will give you a system, and we will say, okay, we are using, say, Jacobi method or Gauss-Seidel method. What is the spectral radius of the coefficient matrix? So then you should know how to first obtain the I'm always telling coefficient matrix. It's the iterative matrix. Okay. So we will give you a linear system. We will use Jacobi or Gauss-Seidel method, or even SOR method, successive over relaxation method. Then we will ask you what is the spectral radius of the iterative matrix. Okay. Then you should know how to compute the iterative matrix of that method for the given linear system. Okay. That is the first thing you should know. Once you have the iterative matrix, you should know how to get the spectral radius of that. Okay. So this is also one important problem that you have to know. Based on this, we may ask either direct questions or some indirect questions also we can ask. Okay, so therefore you should know these things. Okay, and the necessary and sufficient condition is that the spectral radius of the coefficient matrix, no, again I'm making mistake, iterative matrix should be less than 1. Okay. So the iterative method will converge if and only if the spectral radius of the iterative matrix is less than 1. Okay. So therefore, if we ask whether the Jacobi method for this system will converge or not, okay, the best thing is first you look whether the coefficient matrix is a diagonally dominant matrix. If it is so, you can close your eyes and say that yes, it will converge. If it is not a diagonal matrix, it doesn't mean that the method will not converge. You have to go to find the iterative matrix and then find the spectral radius of the iterative matrix. Okay. And see whether that spectral radius is less than 1. If it is less than 1, yes, the method will converge. Otherwise, it will not converge. Okay. So these are some key takeaways from the iterative methods chapter. And then SOR method, you have a relaxation parameter. Okay. Generally, it is very difficult to find an optimal parameter that gives you the maximum speed of convergence. We have seen that. But for certain matrices, you can find the optimal relaxation parameter. We generally use the notation omega for that. Okay. What is that special case? And in that special case, how to compute that optimal parameter? That also you should know. Okay. So these are some of the important topics that you have to understand from this chapter. Okay. We have given many assignment problems based on this. Okay. So as I told, we may repeat some assignment problems in the exam, or we may combine one or more problems and then make a new problem, or we may also ask some new problems which you have not seen in the assignment. But if you know the theory and you have solved all the assignments, surely you can solve them. So the exam will not be very difficult. It will be moderate to easy. For those who have seen all the video lectures and solved all the assignment problems, that is enough for you to get very good marks. Okay. I think we will stick with only objective questions. We will not ask any subjective questions. Okay. Then we have gone to eigenvalue problems. Okay. In this, mainly we discussed power method. In power method, we can capture only the dominant eigenvalue. And there are some technical things that power method needs unique dominant eigenvalue. Then only it can converge, provided it has certain other hypotheses, right? One hypothesis is, of course, the dominant eigenvalue should be unique. And then the next hypothesis is that the set of all eigenvectors of the matrix should form a basis for the vector space Rn. And then we also have the initial guess. So the initial guess that you choose should be in such a way that in its representation with respect to the eigenvector basis should have its first component to be non-zero. Okay, so that's very important. That is C1, we use that notation C1, that should not be equal to 0. If all these are done, then the power method converges to the dominant eigenvalue. So you should know. So many questions can be framed based on these ideas. Okay. We have also given some questions in the assignment. So you should try to see. We have also given some exercise problems in our notes. Okay. So try to see those exercise problems and try to solve them. Some small fill in the blanks questions or MCQ or MSQ questions can be framed from there. So we may mainly frame from these questions only. So therefore, it's very important for you to solve them also. And then in power method, we have also covered inverse power method, shifted power method. Okay, so you should learn to see how you can, where the inverse power method will converge in a very normal sense, and what is the purpose of shifted power method. Okay, so shifted power method is generally used to capture other eigenvalues of a given matrix if at all certain informations are available for us. Okay, those informations and also to some extent the hypothesis of the power method can be verified through a very important theorem called Gasparian theorem. Okay, so it's Gasparian theorem is a very important, very interesting theorem. So you should know at least the statement of the theorem to the extent that you should be able to verify certain hypotheses of the power method. We can generate a lot of interesting questions based on this. Okay, therefore, we have already given some questions, so you can see that. Therefore, Gasparian theorem statement should be very clearly understood. We have also covered it in lecture, so you have to carefully see that. Gasparian theorem can be applied to A in order to verify the hypothesis of power method. It can also be applied to A transpose. Okay? So therefore, if sometimes if the Gasparian theorem applied to A is not working, you should also immediately go to apply Gasparian theorem on A transpose and see whether your required information can be obtained from there. Okay. And then you see what all kind of information that you can see is that whether your matrix has dominant eigenvalue or not. Without knowing the eigenvalues, you can find that whether your eigenvectors are going to be linearly independent. That also in a very restricted sense, you can inform that you can understand it from the Gasparian disk. Okay, another thing is even spectral radius information can be obtained for the iterative methods, okay, by looking at the Gasparian disk. Okay, we have given all the examples for such ideas in our lectures, so you have to carefully go through those examples and try to understand if we give a matrix and ask you what are all the Gasparian disks. This is the plain question that we can ask. Okay. We can otherwise we can ask whether it has a unique dominant eigenvalue. We'll give a matrix and ask whether it has a unique dominant eigenvalue. Okay, or the unique dominant eigenvalue lies in which disk. This kind of questions can be framed somehow. Some fill in the blanks question or something will frame from there. Okay, so therefore you should be very clear with these concepts. Then only you can answer such questions. Okay, so with this, I think we have covered the linear algebra, numerical linear algebra part of our course. And then we went into the non-linear equations, right? So the next chapter is non-linear equations. Here, our aim is to approximate a root of a given nonlinear equation. For some theoretical purpose, we assume that the root that we are interested in capturing are isolated roots, and more into the theory, we also look for only simple roots. When you talk about the order of convergence of the methods, you more precisely want the roots to be simple roots. Okay, then you can talk about the order of convergence of the method also. Okay, yeah. Before getting into nonlinear equations, I would like to just have a break and ask you if you have any questions on the linear algebra part. You can ask us now. Okay, so for the nonlinear equations, we mainly categorize the methods that we covered into two parts. One is the bracketing method, and another one is the non-bracketing or open domain methods. In bracketing methods, we have covered bisection method and regular falsy method. And in the open domain methods, we have covered the secant method and the secant method, Newton-Raphson method, and a general framework called fixed point iteration methods. Okay, so the bisection method and regular falsy method, they are very geometrically very intuitive and very interesting. And these methods surely converge. That is the main advantage of any bracketing method once you are able to start the iteration. Okay. But to start the iteration, you have to locate at least one root of your given equation. That's a main disadvantage of bracketing methods, especially from the implementation point of view. So you have to find at least one interval in which there is you should find one interval in which at least one root lies. Okay. So this cannot be done in automized way. Okay. So one has to somehow find it by trial and error, or manually you just plot it and see where you have a root and things like that. And generally you have to give this information as an input to your code. Okay? So that is something which makes these methods not so robust. Okay? But if you manage to get an interval and you are able to start the iteration, this bracketing methods will surely converge. So that is the main advantage of bracketing methods. Okay, and you should also know how to get the how to generate the iteration for bisection method and regular falsy method. Bisection method, what you do is you have an initial interval, and then every iteration you just chop that interval into half and get two pieces of the initial interval, and then see in which piece of these two intervals you have at least one root. You take that interval and discard the other one. Okay, so how will you decide whether there is a root or not? You will see whether the function changes its sign in that root. That is you will find the value of the function at either end of the interval and see if they have opposite sign. Okay, so if they have opposite sign, then you will decide that that is the interval in which you surely have a root of your equation. Okay, so this is how the bisection method iteration will also go, and similarly the regular falsy method iteration will also go in the same way as long as the algorithm is concerned. But how you split the interval, that idea is different in regular falsy method. Whereas in bisection method, the idea of splitting the interval is just simple. You will just chop it into equally two parts. Okay, that's bisected. In regular falsy method, you will take two endpoints, okay, and then you will draw a line joining these 2 points on the graph, and then you just take the point of intersection of that line with the x-axis. That is the point at which you will make a split of the interval. And again, once you split the interval into two pieces, then the idea of how you will decide which piece of these two should be taken is just to see where the sign change happens for the function. Okay, so that is the idea even for regular falsy method. The advantage of these two methods is that if you manage to start the iteration, that is, you manage to get an interval in which there is at least one root, then surely your iteration will go on and it will converge. Okay. Then in the open domain methods, we covered the regular falsy method now, the secant method, Newton-Raphson method, and fixed point iteration method. And we had in secant method is more or less the same idea. In fact, it's exactly the same idea as regular Falsy method as far as the iteration formula is concerned. But the way you implement is rather very direct. You will start with two, arbitrarily chosen points, and then you will start iterating it without bothering whether you have an interval in which at least one solution lies or not. So that's the main botheration in the regular Falsy method and also in bisection method. Whereas in open domain methods, you don't care about that. You just keep on, you have a formula for the iteration, you will keep on generating the iterations without bothering whether there is any root lying in any interval or not. Okay. So that's the advantage of open domain methods. But the disadvantage is that sometimes the method may fail to exist. That is, they may fail to generate the iterations, or even if they generate the iterations, the iteration sequence may not converge. Okay, so these are all the disadvantages. That also gives us importance of analyzing and understanding when the sequences will converge. Okay, so that is one important task that we have in this chapter. So we have proved secant method convergence theorem. We have also proved Newton-Raphson convergence theorem, and we have also proved the fixed point iteration methods convergence theorem. You should know the order of convergence of secant method and Newton-Raphson method. Okay, so the secant method order of convergence is 1.62 or 56, I don't know. Okay, so that number is there. And then the Newton-Raphson method has quadratic convergence. Okay, and when they converge quadratically, like Newton-Raphson method, when it converges quadratically, if you see, we have used the definition called asymptotic order of convergence. Okay, so as per this, you have limit n tends to infinity mod xn plus 1 minus r divided by mod xn minus r the whole mod xn minus r square. Okay, this limit should be a finite number, which is a non-zero number. If that is so, then the sequence will converge quadratically, exactly quadratically. Okay, we have proved this kind of limit for Newton-Raphson method, and we have also given what is the constant to which this limit converges. Okay, so that is that limit. What is the limit of this quantity? That is mod xn minus r divided by mod xn minus 1 minus r whole square. Okay, so that if that happens to be non-zero, then you will decide that it is quadratically converging. Otherwise, if it is infinity, then quadratic convergence doesn't happen. Okay, when it will become infinity, because that expression will have, I think, f double dash of r divided by 2 into f dash of r. Okay, therefore, if f dash of r is 0, then you won't have quadratic convergence. That is when your root has multiplicity greater than 0. Okay, greater than 1. Sorry. If the multiplicity is greater than 1, then your Newton-Raphson method will not converge quadratically. Okay, so we may frame a question where we'll ask, we'll give some equation, and we will say that suppose the Newton-Raphson method is converging to this particular root, we will actually have that root in such a way that its multiplicity is greater than 1. Therefore, no, then you will decide by seeing f dash of that r. If that is equal to 0, you'd say that it's not going to converge quadratically. Okay, so this kind of ideas can be used to generate some questions. Okay, so you have to be clear about this concept. You may not know the proof of these theorems, because I may not give any weightage on the proof of secant method and Newton-Raphson method, but from the knowledge point of view, it's very important for you to understand it. But just for the examination, it's very difficult to generate any question from here. Okay, but statements are very important. Okay, there can be many questions from the statement of these theorems because the statement itself of these two methods, they are so involved that you can generate many questions, especially order of convergence questions. Okay, so therefore you have to be very clear with the concepts. Okay, and then fixed point iteration method is a very deep concept. As you would have seen, we spent 2 lectures on that. It has a lot of deep concepts, so you have to concentrate more on the fixed point iteration method because for a given equation, writing a correct iterative function itself is a very deep concept. Okay, and then comes its convergence, of course. Okay, but choosing the correct iteration function is something which is a very deep concept, and therefore you have to understand it very carefully. So with all this, I think we have then finished a nonlinear equation chapter, and then we went into the interpolation chapter. I hope interpolation chapter is now running, I think, right? So the week now running, so there's no point in, just recalling what we did in that. So therefore, we will do it in the coming live sessions. So if you have any questions, you can ask us. Okay. So if you want us to give more precise summary of the course in the live session, you can tell us. We can also come with more precise summary. Okay. So if you have any questions, you can ask us. So probably if you don't have any questions, if you have any doubts or you want us to explain something, some particular concept, so you can ask us. We can again revisit those concepts and explain you. If you have some general questions also regarding exams or assignment, or if you have any difficulties, that also you can tell us. Oh, so Ravinder is asking, Dr. Ravinder, thanks for your question. So you are asking how to find the error in polynomial interpolations. You see, error in polynomial interpolation is we have a formula for that. Okay, of course, that formula is not very. You cannot quantify that formula because you have an unknown involved in that. Maybe I will just share the screen and explain how it goes. Open source. Yeah. Okay. Now what I do? Yeah. So you have how to find the error in the polynomial interpolation. Uh, So by definition, see, you have two levels of errors. One is mathematical error and another one is the arithmetic error. I think arithmetic error is released this week or is going to be released in this week, right? The next week. Okay, so that is not a thought. So as far as the portions covered for us so far, it is only mathematical error. Of course, the exact value uh, minus the approximate value. So this is the polynomial and you have the exact value. This is the error. But then you see, this is something which is not going to really give us any idea because f of x is not known to us. That is why we are going for the polynomial approximation, right? Therefore, one has to somehow sense this without going into this direct definition. For that, what we have to do is we have proved a theorem on mathematical error, but of course that also is not strictly speaking, practically it is of not much use because it again involves the not only the function value, but it involves the n plus first derivative of the function. That's too much when compared to even function itself. But then that's the life. Okay, so mathematically, this is what maximum you can tell. Okay, the mathematical error, which is f of x minus pn of x, can also be written like this. That's what the theorem says. Now the question is, okay, it looks more complicated, and also you cannot quantify it because you don't know what is the xi. Okay, now how can I use this to get any information about the error if you ask? Then we have covered some ways to find the estimates. Okay, so we have also given certain examples. Okay, so what you do is you can find the maximum of the derivative, and then you can also find the maximum of this product. Okay, so if you recall, if you the formula is fn plus 1, the derivative evaluated at some xi divided by n plus 1 factorial into that product, right? Now we have given an example where we have taken the polynomial as the linear interpolation polynomial. Therefore, n is equal to 1. Therefore, the derivative will be n plus 1. Therefore, it should be the second derivative. And the product is given like this. Okay. Now, what you can do is, of course, you cannot exactly quantify it. Okay, that's genuine because if you can quantify it exactly, then what is the point of approximation, right? So the exact quantification is not possible, but you can find a estimate for this mathematical error using this formula, provided if you can find a maximum of this function f double dash, modulus of f double dash, and also the maximum of this product. Okay, when it is a polynomial p1 linear polynomial, this product happens to be the absolute value of a quadratic polynomial, right? You can find a maximum of that very easily. And of course, this one has to find the maximum of this. From the examination point of view, we may give you some simple functions like sine function, cos function, for which you know what is the second derivative and what is the maximum of that. Say, for instance, if I give you sine, then its first derivative is cos and second derivative is minus sine. Anyway, you are taking modulus, therefore sine. In the worst case, you can say that sine function in absolute sense, it is just less than or equal to 1, right? So this kind of estimates you can always fit to this part. And for this, since it's a quadratic polynomial, in this particular case, you can easily obtain the upper bound for this. If it is a higher degree polynomial, then you look at the interval. Okay, so that also we have done in the next example. If you see, we have taken sine functions here. Okay, f of x equal to sine x, and we asked you to find the upper bound for the error in P9, ninth degree polynomial. If you go for the ninth degree polynomial, this product, you can see that it is the 10th degree polynomial. If you go for finding the maximum of the modulus of this 10th degree polynomial, that's going to be very difficult, right? But luckily, we are only interested in this interval, 0 to 1, right? Therefore, x, which is coming from the interval 0 to 1, and all these xi's are also coming from the interval 0 to 1. Therefore, modulus of x minus xi will be surely less than 1. Okay, so if you use that clever idea, you can bound this absolute value of this polynomial by 1. Okay, and then, of course, your 10th derivative of sine function, you know how to bound it. Is the worst bound that you can find, 1. You put that and you see nicely, you don't know what is this mathematical error. Sine minus P9 of x, we don't know. But still you can say that whatever may be this number, it cannot be more than this. Okay, it's pretty small. So therefore, you see, P9 is approximating sine function pretty well. That's what we could infer from this analysis. Okay, so this kind of analysis is what is possible through this kind of formula. Okay, otherwise you cannot quantify it exactly. So that's the problem with this with the interpolation. That's life. Okay, so you have to live with that. Okay. I hope I have answered your question. I don't know how to come back to. Yeah. So Dr. Ravinder, so I hope I have answered your question. Okay, so good. So any other question? I think they also get our streaming little late. There's a lag. Fine. So, okay, so we are nearing the ending time of our live session. So if you don't have any other question, probably we can end the live session now. Just wait for 2 minutes. If there is no other question, we can end the live session. And thank you for your time. Okay, so shall we end?
Yes.
Okay, so once again, thank you everybody. So we will meet in our next live session and see you. Bye. Done?